Real systems have usually nonlinear properties. As a consequence, also, many mathematical models are such nonlinear descriptions. But in engineering practice, also linear mathematical models are very popular as they can frequently be used as a reliable approximators of nonlinear models for the near neighborhood of the chosen operating conditions. Such working conditions are called operating point. There are many procedures which can be used to generate linearized model from a nonlinear one. Let's present one possibility which is available also in Simulink and MATLAB program environment. Let's define first a mathematical model of nonlinear system as is given with the equation 3.1. Each variable of nonlinear model can be, without loss of the generality, represented by their values in the operating point and by the deviation of the variable from this value as is presented with the equations 3.2 and 3.3. Operating point is indicated with the overline and deviation from the working point with delta before the variable. Let's take into account that input signal to our nonlinear system in operating point is equal 0.2. We would like to generate a linearized model regarding chosen operating point so that delta signals of nonlinear and linearized model would be as similar as possible. For the presented nonlinear model, corresponding simulation scheme SimModel 8.SLX was developed first as is presented in this figure. Then, simulation run was executed using script file myfile8.m. Command lines inside this file also plot input signal and corresponding output response. The result of execution of myfile8.m is a figure as is presented here. From the nonlinear model response presented below with the blue color, it is clear that velocity of the response as well as the gain depends on the range of the system operation. For the linearization purposes, the simulation scheme SimModel 8A was generated from previously presented SimModel 8 so that generators of input and time signals as well as all blocks to workspace were deleted first. Then one input port and one output port were added into the scheme indicated the location of model's input and output signal. These two elements can be found in the group Ports and Subsystems in the Simulink library. In the next step, existing myfile8.m was extended with the following lines, where UP presents input signal in operating point and YP is output signal in the operating point. It is important to mention that in operating point our system is in equilibrium. For the linearization purposes we have used then the function lineMod, which generates linearized model in the state space form, namely corresponding matrices A, B, C, and D. Inputs to lineMod function are in our case the following. First, the name of the simulation nonlinear model with imports and outputs. The second and the third input are state and input signal in chosen operating point. As our system is of the first order, the state and the output can be chosen as equal signals. From the state space form also transfer function is generated. For testing purposes, additional simulation scheme SimModel8B point SLX was generated as is presented here. In this case, block state space was used for the linear model realization, as in this form the result from the function lineMod is expected. To the input and to the output signal of this linear model also the operating points were added because we would like to compare these two signals with the signals of the nonlinear model. In the myfile8.m, the simulation run was realized for the linear model first, and then the signals were plotted in the previously generated figure. By executing myfile8.m, the linearized model is calculated as is presented by the equations 3.4 and 3.5. And in this figure, the responses of the linearized model are presented with green dotted lines. From this, the following can be concluded. For the small changes of the input signal delta U, the linearized model is a relatively good approximation of the nonlinear one. The successfulness of such approximation may sometimes be improved by the use of parametrization or even optimization. Of course, by the increasing the distance from the operating point, the quality of the approximation decreases. For the good approximation of the nonlinear model with the input signal, for instance, 0.6 in operating point, the repeated linearization with the change conditions is justified. The purpose of the model use can suggest which version of the obtained linearized model is the most appropriate one. Homework. For the linearized system description, the proportional integral controller was designed as is presented with the equation 3.6. Using simulation, compare the closed-loop responses of the linear and nonlinear model as is suggested by these two block diagrams and comment the obtained results.